I'm going to cover two sections today. One of them has to do with, the first one has to do with multiplying and dividing rational expressions. Okay, so what we did on Monday was we simplified them, found common factors and canceled out factors, and put the domain restrictions that need to be explicitly stated. Today we're going to look at multiplying and dividing rational expressions. That's section 6.2 in the book. And then the next section, which we'll talk about at the end of the class, is going to be 6.3, which is adding and subtracting rational expressions. And actually the dividing rational expressions we're going to kind of revisit a little bit later as well. But for now, let's look at it in the context of multiplication. Okay, so let's say we have u, v, w, and z, and that can represent anything, a real number, a variable, any kind of algebraic expression, but just some placeholder. If we're multiplying two rational expressions, ratios of those values, u, v, w, and z, to multiply them, we just basically multiply the numerators and denominators, just as though it was a fraction. Like 1/2 times 2/3 is 1 times 2, that's 2 over 6, right, 1/3. So the only restriction here is that v can't be 0 and z can't be 0, right, because then we have division by 0 and the whole thing just doesn't hold together. So oftentimes these things almost look nearly trivial, right? When we have something like this, that's 6x over x minus 2 times x minus 3 over x squared, when we combine them, it looks just like combining the factors, that there's not too much of a difference there. We just multiply the numerators, multiply the denominators, and then we look for common factors, see what can be factored out and canceled. And in this case, we have an x that's in common in both the numerator and the denominator, so that just cancels out. Now, we canceled that out, and now we have to ask ourselves, did we get rid of an implicit domain restriction? And we did not, because we still have an x in the denominator, so x can't be 0, and that's implicitly stated there. Okay, so if we take a look at another one, now this first one looks like just a polynomial, right? 4 minus 2x. But in fact, any expression can be represented as a rational expression just by putting it over 1, right? So we have 4 minus 2x over 1 is one way to look at it. So whenever we have just a polynomial or any kind of expression like this, we just multiply it into the numerator and we get our solution. So in this case, we look at it as 4 minus 2x over 1, and multiplying them together, we get that expression, and we notice that we have a 2 minus x. If I factor out if I notice in this expression here, I have a 4 that I can, or a 2 that I can factor out, so that actually becomes then 2 times 2 minus x. I have in common a 2 minus x in both the numerator and the denominator, so when they cancel, I just get this expression 2 times 2 plus x, and since I lost one of the implied domain restrictions, I have to explicitly state it now, and so x can't be 2. All right? Any questions? Yes? It can't be 2 because what I factored out was the 2 minus x, and so if we have 2 in there, we have 2 minus 2. Okay, so try one. Actually, try 2. Okay, so how you doing with it, okay? A little confusing? All right, so let's just step through these then. Okay, so the first thing we do is we just combine the numerators and the denominators by multiplying them together. So in most cases, you just wrap it in a parentheses and put them together. Now what I did here was I made a little change. I'm anticipating that this 6x minus 6y is going to somehow interact with this x minus y, and so what I'm doing is I'm factoring out a 6, and so I just multiply the first 4x squared times y, and then multiply that by what I've, that second term, which is now 6 times x minus y, and keeping that in parentheses so I keep my order of operations right. All right, then in the denominator, all I did here was I just changed the order, and feel free to do that. There's nothing wrong with it, just make sure that you're writing all your terms. Sometimes it's just a little easier to see what you're doing when you do that. So when I compare the numerator and the denominator here, I have an x squared in the numerator and an x in the denominator, so one of those x's can go away. I have a y in both the numerator and the denominator, so that's going to equal 1 when y doesn't equal 0. And then x minus y is both in the numerator and the denominator, and so those will cancel. So then if I look at my coefficients, I have 4 times 6 divided by 3. Now, the tendency is always to want to multiply before you divide, but divide first because it's easier to do. 6 divided by 3 is 2, 2 times 4 is 8. That's a little easier operation than going 4 times 6 is 24 divided by 3 is 8. You get to the same place, but you know, always, I don't know, for me it's always nice to work with smaller numbers. You just make less mistakes. So recognizing those things that I just pointed out, I'm going to get just an 8x remaining. So just to go through here, the coefficients, the 4 times 6 divided by 3 reduces down to just plain old 8. The x squared and the x, one of the x's cancels, and so I just have an x left over. And then I have this last term of x minus y, and that cancels. So the only thing really that carries over into the answer here is 8x. And so I have to note my domain restrictions because I do have an x and y in the denominator, so I know that neither of them can be 0. And I have this x minus y, and I know that can't be 0, so the only way that x minus y is 0 is if x equals y, and so we can't have that. So we have to say y cannot equal 0. So there's our solution there. So we mush it all together, we look at the factors. Now if you're more comfortable doing this, you can cross out your factors, do it like this, and cross out the y's and cross out one of the x's and do that. That's okay. Okay, if that's a way to keep track of it, then you can see that the only thing that I have left over, dealing with the exponent, I just meant to cross out the 2, not the x, and I have to cross out the x and the y down here as well. So it's easier to see sometimes what you end up with. But that's just a personal preference. There's nothing wrong with keeping track that way by canceling them out. Remember, what you're doing when you're canceling is you're really just factoring out a 1. So when you have an x minus y over x minus y, unless that's 0 over 0, that's a 1. So that can be just taken out, because any number times 1 is just the original number. So we can, when we're canceling out, we're just really removing a factor of 1. Now let's look at the second one. Okay, this second one, you notice there's a certain amount of symmetry to it. You have an 8 minus z and a z minus 8. All right, so we can factor out a negative 1 if we want. So when we take those together, I'm going to factor out a negative 1 from that top 8 minus z, and I get z minus 8. And now I have something that looks like all of these terms now match up. And so I got z minus 8 on both the numerator and the denominator. I got z plus 8 in the numerator and the denominator. And so all I end up with is that negative sign. So when all your factors cancel and you just have either no sign or a negative sign, that's either 1 or negative 1, right? So this is just going to equal negative 1. But it only equals negative 1 when over a certain domain. And that domain can't include z equals 8 and z equals negative 8, because otherwise we end up with 0 over 0. And that's definitely not equal to negative 1. Okay? I see some people not quite so sure. The negative came from the fact that when I looked at this, I see an 8 minus z, and I look down here and I see a z minus 8. So the 8 is positive up here, negative down here. The z is negative up top, and it's positive down here. So I know if I multiply, I can factor out a negative 1 and turn one of them around. So this z minus 8 used to be 8 minus z with a negative sign in front of it. So if you distribute that negative sign, you'll see you get negative z plus 8, which is just commute it and you get the other way around. Okay? Now, dividing rational expressions works a whole lot like multiplying. And here it's just a recognition that division is the same as multiplying by the reciprocal. Okay, so if I state this in the way I stated the earlier rule, we have u, v, w, and z that can be real numbers, variables, algebraic expressions, anything. So when I divide it in this fashion, I use that division sign. What I really, first thing I want to do is I want to change that into a multiplication sign. And you see what I did? I turned over the w over z is now z over w. That's the reciprocal. So think about what happens when you have not a real explicit kind of rational expression, like if you're going to say that this is divided by, let's say, x plus 2, that's going to be the same thing as multiplying by 1 over x plus 2. And vice versa. If we are dividing by 1 over x plus 2, that's the same thing as multiplying by just x plus 2. Okay, you see how that works when you don't have really the ratio set up the way you would expect it. You still take the reciprocal, you just kind of add the fact that this is x plus 2 over 1. All right, but there's a further requirement here now. Remember, we have the domain restrictions, and if we just look at this, it's pretty obvious v and w can't equal 0. But since we started out with this w over z, we have the additional restriction that z can't be 0 either. And so when we do the multiplication out, we have to remember that v, w, and z can't be 0. The only one that can be 0, and it's perfectly fine if it is that u can be 0. If u is 0 and the other three are not 0, then your expression equals 0, right? Because 0 divided by any number, or 0 times any number, is still 0. The only thing you can't do with 0 is divide by 0. And so in order to avoid that, you have to state that v, z, and w can't be 0. Okay, so let me show you an example. So we have this x over x minus 2 divided by x plus 1 over x plus 3. So the first thing I'm going to do is I'm going to take the reciprocal of that second one, and I have x plus 3 over x minus 2 and x plus 1. There's no simplification possible here, right? All these factors are unique. So I took the reciprocal of this, and so it's implied that x can't be 2 and x can't be negative 1. But what's not implied here is that x can't be negative 3. So you have to state that explicitly. So here's a case where even though I didn't remove any factors, by taking the reciprocal, now I have something in the numerator that in its own right probably could be in the numerator, but once it was in the denominator, that means that that can never be 0. So the implicit ones are x can't be 2 and x can't be negative 1. And so it's not necessary to write those. All right? All right, so let's go through a couple more examples. Let's say I have x squared minus 1 over x plus 2 divided by x plus 1 over x plus 2. So I'm going to take the reciprocal, And I'm going to factor that x squared minus 1, because I'm going to anticipate that I'm going to be able to do some canceling. So you see this, this x plus 2 in the numerator comes from the denominator, and then this x plus 1 down here comes from the numerator of that second rational expression in the problem. All right, now we can cancel the x minus 1 and the x plus 2, and we just get x minus 1. But here again, we have to explicitly state what our domain restrictions. And so we go back to our domain restrictions. We know that x can't be negative 2. All right, otherwise we have a division by 0 here, and x can't be negative 1 because then we would have division by 0 in this other form. And so we state those as domain restrictions. All right, yet another one. So here we have a couple polynomials, and the first thing we should be thinking about is taking the reciprocal, and while we take the reciprocal, we can put in the factored versions of those polynomials. So what I want to write is I want to factor out the 5 from that 5x plus 5, then I'm going to factor that x squared minus 3 and get did I factor that right? It's just an x comes out of there. I didn't factor that right, did I? Shouldn't that just be this should be let me see how I can undo this. This should just be an x, right? Because if I multiply, oh, I'm completely mistaken. I'm sorry. This was right, and I'm at fault for doing too much at once. What did I say this was? X plus 1, right? This is the denominator. Let me catch up to where I am. X squared minus 2x minus 3, if I factor that, I get x minus 3 times x plus 1. So that's now in the numerator. And then this, what was in the numerator, factors to x times x minus 3, and that's why that's in the denominator here. Okay, so I apologize. I just didn't read my own work right. Okay, so actually I'm going to rewrite this on the board, not skipping the step that I skipped here. So the problem was 5x plus 5 over 2x divided by x squared minus 3x over x squared minus 2x minus 3. So I'm going to rewrite that as a multiplication. And so I'm going to take the denominator here, and I'm going to start using parentheses so I can eliminate this. And then this on the bottom turns out to be x squared minus 3x. And then what I have as my second step was I factored these now. That first term here factors to 5 times x plus 1. This thing here factors to x plus 3, excuse me, x minus 3 to and x plus 1. Okay, so that's what this factors to. This doesn't factor. And then this one factors out, I can factor out an x, so I get times x minus 3. Okay, so that's what I end up with here, and that's the way I did it. So I skipped this step, and I confused myself when I was explaining it to you. All right? Does that make sense? Okay, so now we cancel out what we got to cancel, and we see that we have a common x minus 3 here, and the x plus 1, we can indicate that as x plus 1 squared, and we make this those two x's 2x squared, and then we look back at the original problem to see where are the domain restrictions. Well, the domain restrictions are such that x can't be 3 and x can't be negative 1, because that would make these two factors 0, and remember that those two factors came from the denominator, so those can't be 0. Now, the fact that x can't be 0 is implied with this one, so we don't have to indicate that separately. Awful lot of skeptical looking faces there, yes.
The person at the top one,
Yeah.
the x cannot equal -1 and x cannot equal -2 was already implied.
Uh-huh.
So why did we write that if it was already?
You don't have to.
Okay, so then what would the restriction be then?
The restriction on that one is that, well, you do have to write that x, actually, I think you do have to write it. Because if we go back to that one, all we have left is this x minus 1. So that means that if we just left it like that, x can be anything. But if we look at this original one, we say that x plus 2 can't be 0. So that means x can't equal -2. And then when we took the reciprocal, we also had an x plus 1 in the denominator. So we have x cannot equal -1. So those do have to be stated because they're not suggested in the final reduction. Okay?
Mm-hmm.
All right, any other questions? Okay, so of course, time for you to try one, or two. These I will ask somebody to come up to the board and do, so give these a good shot. Okay, so while Haley's writing that second one, I'll catch up on my charts. And there we go. Okay, write out the answer, don't just cancel it out, okay?
Okay. Sorry.
Almost. Now, x plus 5 can't be 0, so that means x can't be -5,
Okay.
right?
Yeah.
Because if you plug in a -5 to what you canceled out, you'll get 0.
Uh-huh.
And then you have 0 over 0. So it has to be what makes that expression x minus 5 equals 0, or x plus 5 equals 0. So the solution itself is right. The only thing missing was the domain restriction. So you can see in my slides I get the same thing. X can't be 0 as well because we have the x in the denominator here. So we need one more domain restriction. X can't be 0, right? Because then we would be dividing by 0 in both of these. Make sense? Lou, you follow that domain restriction?
Yeah.
Can you explain to me why it's a negative?
Yeah.
Sure.
Because if you were to put it in the denominator, you plug that in, if it's 5, that equals 0, 5 minus 5 will be.
This one's fine, okay?
Yeah.
If x equals 5, then we do have 0, but that makes that an implied domain restriction. The one that's not implied, it's implied here, but since we've eliminated it, this is the one that we're writing the domain restriction for, not this one. This one's implied, so we can leave it alone. It's the one that we need to add in from this.
Since we got rid of it, you got
Yeah.
Okay.
Okay, so whatever's implied at the end, you know, somebody would look at x over x minus 5, and you know you get division by 0 if x equals 5. What you don't know is that you would get division by 0 if x was -5, because if you put in -5 over -5 minus 5, that's going to be -5 over -10. Looks like a perfectly good number, but from where we started, it can't be, because then we're actually saying 0 or not a number. I guess it's okay from this standpoint, here we got, you know, 0 divided by 0 is not x over minus 5, or x over x minus 5, I mean. Okay? All right, now let's talk about adding and subtracting. Adding and subtracting rational expressions works very much the same as adding and subtracting fractions. Okay, so when we have something with a common denominator, so here in this case my common denominator is w, you just retain the common denominator and you either add or subtract the numerators. Okay, so if we were talking about u, w, and v being just ordinary numbers, if we took 1/5 plus 2/5 equals 3/5, right? The fifth, the common denominator would stay, and we would just do the operation with the numerator. So if we, actually I think this went a little further than I wanted to. Anyway, I got this x divided by 10 plus x plus 2 over 10, and so all I have to do here is add the numerators, or yeah, x plus 2, and then I simplify them by taking 2x plus 2, and then I notice that I can divide these things out. If I factor out a 2 in the numerator, factor the 10 to 2 times 5, I can cancel out my 2's, and I get 8x plus 1 over 5. I've never had any variables in the denominator, so I don't have any domain restrictions. And in fact, if that common denominator had a variable, it would be retained and we would have an implied domain restriction. All right, now I'm going to use this as an opportunity to look at things like this, okay? And I'm going to say, what if we ended up with something like this? This 2x plus 1, this is different than my example here, divided by 2. I see this a lot, and I know that oftentimes you understand that you can't do this, but oftentimes just in the hurry of things you make this mistake where you say, oh, the 2's cancel and I get x plus 1. This is not right, okay? You have to make sure that this 2 is dividing every single term in that expression, that you never do division what I call term-wise. What you do is you only do division factor-wise. So what I did up here, where I had the 2x plus 2 and then the 10, I factored it, and so now I have multiplication where it's 2 times x plus 1 over 2 times 5. Then you can cancel. Be really careful with this. I can't tell you how many times I see that, and I know the person who's doing it knows better than that. In fact, when I've gone over tests and quizzes with people, it's one of those slap the forehead kind of things that says, oh yeah, I knew that, but you tend to do it when you're in a hurry. So just be very careful when you're dealing with these things. Always cancel factors, not terms. Okay, so we'll look at another one. So here we have a common denominator of n times n plus 2, and we have 3 minus 2n minus in the numerator for one of them, and then we have 1 minus 3n in the numerator of the second one. And notice this is subtraction now. Now subtraction is another one of those little minefields that you have to kind of tiptoe around to make sure that you don't end up with something wrong. And so, I don't know, I think I've said it before, and it's not really, it's kind of an absurd little saying, but parentheses are your friends in these situations. They really help you out. You can write parentheses around all the numerators and just put the operation in the middle, and what that allows you to do is to make sure that you're going to count this double negative properly when you start to simplify. So you do one step at a time. Put it in parentheses, then distribute the negative sign. So when I do that, I get the first set doesn't change, 3 minus 2n, and then the negative makes it negative 1, and the negative 3n makes that positive 3n. And so when I collect my common terms, I get 2 plus n over n plus 2, and suddenly I can see that I have a n plus 2 in both the numerator and the denominator. So now, if I put parentheses around that, you can see that that's actually, these are the same factors. So I get 1 over n, and since I've eliminated the n plus 2, I have the domain restriction that n cannot equal negative 2. So here's one, even though I had a common denominator, part of that denominator disappeared on me, so I have to make an allowance for the fact that I have to now explicitly state that n can't be negative 2, otherwise we're dividing by 0. All right. So that's straightforward enough. How about making a common denominator? So when you're dealing with numbers, oftentimes people will just take the denominator outright and multiply those together to make the common denominator. And though you end up with a larger number, that generally works. Okay, so if you're trying to add something like 1/12 plus 1/20, you can use a common denominator of 12 times 20, which is 240. But it's unnecessary. Okay, you can actually use something called the least common multiple. And so if we have something that's over 20 and over 12, we look at how this factors, okay? And so I'm just ignoring the numerators right now, and that's why I put the little squiggles. 20 factors into 2 times 2 times 5, 12 factors into 2 times 2 times 3, and so the 2 times 2 is common in both of them, so I only use that once, and then the unique factors are 3 and 5, so I use them, and so when I multiply it, I get 60. So the appropriate common denominator in these fractions would be 60, not 240. You see, it's 4 times as much. Now with numbers, that's not so bad, because you can usually use a calculator, or you can factor it out and cancel. But with polynomials, it's very difficult, because you're going to end up with polynomials that are a much higher degree than necessary, and when you have a high degree polynomial, like an x to the 5th or something, those are hard to factor, while an x squared, you can tell pretty readily whether you can factor a polynomial that's only 2nd degree. Okay, so the same thing goes with common denominators in when we're using expressions. Yes?
Why did you get 60?
60 because I multiplied 2 times 2 times 3 times 5. The 2 and 2 were common in both of them, so I only use it once. Okay, so I'm only going to use factors once. I use the ones in common once, and I use the unique ones once. So in this case here, my denominators are x times x plus 2, and then x plus 1 times x plus 2. So I do have an x plus 2 in common, so I'm only going to use that once. And then I'm going to take the unique factors from each, which are x and x plus 1, and that's going to be my least common multiple. Don't feel like you have to multiply these things out, because ultimately when you're going to try and cancel and reduce these things, you're going to just turn around and factor it anyway. So this is really what you want to do, is use the least common multiple of these common factors. If you use that x plus 2 twice, then you have an x plus 2 squared, and you're going to end up with a much higher degree, or you're going to end up with a degree that's one more than it needs to be in the numerator. Okay, so just try finding the least common multiple here. Like if these were the denominators of fractions, what would be the common multiple, the least common multiple between 18m squared and 45m? So how do they factor? Anybody? Yes?
What 18 give you 2 times 3?
Almost.
Wait, no, 2 times 3 times 3.
Yeah, right, okay.
And then and 45 is 3 times 3 times 5.
Yeah, okay, so then,
And they both share an m.
and they both share an, so the least common multiple then would be the 2 times 3 squared and the 3 squared times 5m. The m squared goes there, not just the m, because
Okay.
you have an m in common, but then you also have that other m as a unique factor. Okay, so we want to include all the common factors and all the unique factors. So when we have a variable like that, we just go ahead and take the highest degree.
Okay.
And then, of course, we only use the 3 squared once, and then we use the 2 and the 5. So when we combine all that stuff together, we get 90m squared. Okay. So let's look at adding with an unlike denominator. And so we'll start out with just this 12 and this 20, which I've already shown the common denominator would be 60, right? So it's handy to have that factoring around because it tells you what you have to multiply to get the common denominator. So for 12 to get to 60, we're multiplying it by 5, right? And so we're going to multiply, here's my factoring. So I'm going to multiply the 5x over 12 times 5 times 5 over 5. So basically what I do, since I'm looking at this one here, this 2 squared times 3, I look at what's unique in the second one. In this case it's 5, and I multiply it by 5 over 5. I'm not changing its value because I'm multiplying by 1 ultimately when you do 5 over 5. Okay, and then the second term, if I look at the 20, what's unique about the 12 is the 3, so I'm going to multiply the 20 times 3 to get to 60, and so I have 3 times 3, and when I work all that out, I get 25x plus 9 over 60. And then you ask yourself, does that factor? And it doesn't factor because 25 is only 5 times 5, and there's no 3 in it. There's no 5 and a 9, and so there's nothing that we can factor out. So this one is done. Okay, so let's try one with a polynomial now. So we have 5x over x squared minus 1 plus 3 over x squared plus 2x plus 1. And we get 5x over, and I'm going to factor that x squared minus 1 to x plus 1 times x minus 1. And I'm going to factor that x squared plus 2x plus 1 to be x plus 1 squared. And so my least common multiple is I'm going to take x minus 1 times x plus 1 squared, right? Because I have one of the x plus 1's in common, but I have an extra one in here, which makes that a unique factor. So when I multiply them all together, I get this as my least common multiple. Okay, so I'm going to take this first factor, and I had x plus 1 times x minus 1, but my least common multiple has that other factor of x plus 1, so I'm going to make that squared and multiply that x plus 1 in the numerator. And then I didn't have an x minus 1 in the second one, so I have to multiply that denominator by x minus 1. And of course, to keep everything balanced, we do this x minus 1 on the top. And then it's a matter of extending this. So the numerator or the denominator stays the same, that x minus 1 times x plus 1 squared. And then I just multiply out and I expand the numerator. And I do that so I can collect common terms. Okay, generally we're not expanding things that are factored, but since we have this kind of thing going here, we do want to expand it so we can combine this to then be 5x squared plus 3x plus 2. And then you ask yourself the question, can that be factored? 5x squared plus 3x plus 2. Okay, so how do we determine if that's factorable or not? Well, let's go through that process of factoring by grouping. 5 times 2 is 10, so there's only a few ways to get to 10. 1 times 10, 2 times 5, and that's really it, right? None of them, when we add them together, since they're all positive, equal 3, so we're sure that that doesn't factor, because it doesn't factor by grouping. Okay, so at this point we're done.
Can you just like cancel out the x minus 1 and the x plus 1 in the earlier step?
Where, here?
Yeah.
If you're canceling it out, you're going backwards. You're going back to this.
Okay.
Okay? So the important thing here is that you want the denominator to be the common one. And you do whatever it takes to make it that common one. And that's why you multiply both top and bottom. And so, in fact, if you go backwards on these, you can always cancel out and get back to this expression. Okay, so here's one for you. And let's see, it's about 1/4 past, and yeah, we have a few to try here, okay? So let's kind of work these together, all right? I'll give you some homework on these, but just so we go through all the examples, I will march through these, even though I'm designating these for you to try. So what would you suggest as the common denominator on the top, on the first one?
X plus 3, X minus 2.
Yeah, it's just the product of the denominators because there's nothing in common. And then the numerators just get multiplied by those factors. We expand that, you see that x minus 2 up here comes from the fact that I have x minus 2 times 1. And then this 5x plus 3 comes from the fact that I have to take x plus 3 times x plus 3 over the denominators. And so then I get my simplified expression here. 6x plus 13 doesn't factor, so I'm done. This next one, what would be the common, least common multiple?
X plus 4.
X plus 4. And what do we do with the 25?
You multiply it by X plus 4.
Yeah, you multiply it by x plus 4, and then you have the 10, and that's all over x plus 4. And so when I extend that out, I get 25x plus 100 plus 10, and then that simplifies to 25x plus 110 over x plus 4. And even though we can factor that 25x plus 110, we know it's not going to factor into x plus 4, so there's no point in doing it. I mean, you can, but there's no real point. Okay, so now we're going to do a division here. So the common denominator is going to be similar to the first one, where we'll take the two factors and multiply them together. And then here I'm multiplying that second expression over here by x plus 4 over x plus 4, but I have this negative, so I'm putting it in parentheses and retaining the negative, and then I'm distributing that negative here. So then when I have to simplify, I have x minus x, which is 0, and then 2 minus 4, which is negative 2. And so there's my result then. All right, and then the very last, this is more to try. I'll just post this. It has essentially more of the same, more examples. If you want to, look those over, and those will be fully worked out. Okay, note on the last one, the domain restriction. There's an x does not equal negative y, and that's because I had an x plus y cancel out. Okay, have a good weekend. Thank you.